Hello everyone, and welcome to this video that looks at a specialist mathematics problem associated with vector geometry and planes. So we're given a question. The equation of a plane is given as 2x take y plus 4z equals 6. Again, that's in the general form of the equation of a plane, which is ax plus by plus cz equals d. And we're told that there's also a line as well in space, and it has, and as you can see, we're given an equation in parametric form there. X equals 2 plus t, y equals 1 take t, and z equals 2 plus 2t, where t is a parameter. And the first question asks, what is the direction vector normal to the plane? So we're mentioning that we've got a plane surface, and we're looking for a direction vector which is perpendicular or normal to that plane. And it's a property of the actual equation of a plane that the coefficients of a, y, and z actually form the normal vector. So we can do this as d, for example, d vector, and we can write this as 2, negative 1, 4. And that's our actual direction vector for normal to the plane. So again, it's just the general form for the equation of the plane. We're just taking out the coefficients there. The coefficient of x is 2, the coefficient of y is negative 1, and the coefficient of the z term is 4. So now state the direction vector of the line. So now we're not considering the plane, we're considering the line, which might be somewhere out there, for example. And we've got a line just in space, and the key thing to look at with the direction vector is just to look at the parametric form and actually look at the parameter. If we ever look at the coefficients for our parameter, we can actually get a direction vector. So we can generally write a direction vector as dv. And if we have a look at it, obviously the coefficient of our parameter t for that x equation there is 1. So we can write that. We've got 1. Then for y it's going to be negative 1, because again, it's coefficient of the t there. And then for z or z, it's going to be 2. And we have a second vector there. So now it's asking us to find the acute angle between the line and the plane. Well, we've got the direction vector and we've got the plane. So what I'm going to do is I'm going to actually move down the camera a little bit so we've got a bit more space, because this question, as you can probably tell, is a little bit longer. And we're actually going to consider this geometrically. What's actually happening in terms of vector geometry here? And it's quite straightforward. We have a plane and we have a normal to that plane. We also have a line. See, so there's our normal to the plane. I've just drawn the actual little square on the other side. And then we've got our direction vector, which essentially shares the same direction as our other line equation, other equation of a line in space. Again, this isn't necessarily to scale or anything. We can see them joining with an included angle there. And what we can actually do here is use a formula in order to find that internal angle. And then from there we can actually find this angle alpha down here, which will actually be the actual acute angle between the line and the plane. So we're finding the included angle between the normal vector and the direction vector, because again, the direction vector is the same direction as the equation of the line that we're given in the question above. And so because we're looking at this included angle here, we know that we can actually use a formula that we've come across before to find theta and hence find alpha. Again, this is just a direction vector, so it makes sense. If we use the direction vector to find the angle alpha there, we're finding the acute angle between the line and the plane. So cosine theta is going to be equal to the dot product of our direction vector with our normal vector. And then this is going to be over the magnitude of our direction vector with our normal vector. Excellent, so we can work out the dot product between these two vectors, again, because we're looking at the included angle there. And we know that the dot product, in this case, is going to be 2 times 1 for the x component. Again, we just multiply our components together and then we sum them. And then we've got negative 1 times negative 1. And then we've got 4 times 2. And again, it's just based on the standard dot product formula, doing the dot product of those two vectors. and then that's going to be over the magnitude. So for dv, we're obviously going to have 1 squared, which is just 1, plus, and then we're going to have 1 squared again, which is just 1, and then we're going to have plus 2 squared, which is 4. And then that's going to be multiplied by the magnitude of the normal vector, and we know that 2 squared is going to be equal to 4, that 1 squared is still going to be equal to 1, and we know that 4 squared is going to be equal to 16. Now we can start our simplification on our quest to find theta. And in this case it's going to be 2 plus 1, because again, negative 1 make 1, and then add on 8. And what we can do is we can actually simplify the bottom part. So we know that 1 plus 1 is 2, plus 4 is 6. So we're going to have square root 6 times, and then we're going to have square root 21, because 16 plus 4 plus 1 is 21. So what we essentially end up with is that. Okay, and we can simplify this down further. So we've got 11 on, and then if you know your 21 times tables, that's very good. If you don't, you can use a calculator. You should find that that is 126. Then from there, we can find theta. Theta equals inverse cosine of 11 on 126. So if we find it, from memory it should be about 0.2 radians, but we'll just double check on our calculator. So hopefully you have it in radian mode. Of course you can use degrees if you want, but we put it in to our calculator using correct brackets and surds where applicable, and we should find that to 3 significant figures it is 0.201 radians. Excellent, but now we need to find alpha, because we found the included angle. We want the angle between this line, which may not necessarily actually be exactly like that, but that line and the actual plane. So alpha is going to be pi on 2 take theta. And the reason behind this is, well hang on, this entire angle here is going to be perpendicular to the plane, because that's a normal vector, perpendicular to the plane. So we're going to have pi on 2 radians, or 90 degrees if you're using degrees, as that entire angle there, which is theta plus alpha. So again, it's just a matter of rearranging. We find that alpha equals pi on 2 take theta. So in this case, we can use our calculator to get an approximation for the angle in terms of radians, or if you want, in terms of degrees. And we should end up getting something along the lines of 1.37 radians to 3 significant figures. And that is the acute angle between the line and the plane. So again, relatively straightforward question. You just need to know what's happening. So again, it always helps to actually draw out and think about what's happening conceptually, and then from there just applying the mathematics as you see fit. Have any questions? Leave them below. Thank you for listening.